Now that we've talked about some of the basics of flexure and we've gone through an example in which we solved for the location of the plastic neutral axis of a singly symmetric shape, I'd like to discuss one more concept called the shape factor before we jump into our next example. So we normally designate a shape factor with the letter alpha, and all the shape factor is a measure of how efficient a particular cross-section is in flexure. We look at it as the ratio of the plastic section modulus to the elastic section modulus, which is the same thing as looking at the ratio of the plastic moment to the yield moment. So I'd like to go through a very short exercise of solving for a shape factor. And to do that, we're going to look at our rectangular cross-section again, which has a height of h and a width of b. So for that particular shape, S sub x, the elastic section modulus, is my bending moment of inertia divided by c, and since we're doing this for the strong axis, there's my neutral axis. I sub x is just bh cubed over 12 for a rectangle, and c is the distance from the neutral axis to the extreme fiber, which in this case is h over 2. So my elastic section modulus is just bh squared over 6. Now we already solved for my plastic section modulus, which is bh squared over 4. And so I can solve directly for alpha as bh squared over 4 divided by bh squared over 6, which is equal to 1.5. So this tells us a measure of how efficient a rectangular cross-section is in flexure. And for reference, an I shape is usually going to have an efficiency or a shape factor of about 1.2. Okay, so now we're going to move into example 6-2, which is a little bit of a longer example where we apply some of these concepts to another singly symmetric shape that's a little bit more complicated than the one we looked at in example 6-1. Now we actually looked at this particular cross-section back in our very first lesson plan of the semester. This was examined in example 1-1, and we went through some quantities calculating the bending moments of inertia, the section modulus, the radius of gyration, and so on. And at that point, those quantities may not have made a lot of sense because we hadn't learned how to apply them yet. But now I think those quantities should be making more and more sense. And we're going to continue with this example as a jumping off point to look at some of these other concepts, such as the plastic moment. But I would like to quickly point out some of the quantities that we had calculated back in lesson plan 1. We had calculated the location of the elastic neutral axis, which is right here in our figure, and that is our y bar quantity, and we found that the elastic neutral axis was located 9.4 inches from the top of the top flange. Then we calculated the bending moment of inertia about that strong axis. So my x-axis is right here. My weak axis is the vertical axis. So calculating I sub x, we found that it was equal to 3,570 inches to the fourth. Then we use those values to calculate the section modulus to the bottom fiber and to the top fiber. So we have two values for S sub x, depending on the different distances from the elastic neutral axis to the extreme fibers. And then we calculated a radius of gyration of 8.45 inches, and we have been more often calling that R sub x. Okay, so that is a very quick review of what we had done back in lesson plan 1, and we're going to consider this same shape, and we're going to solve this time for the location of the plastic neutral axis. So now we know where the elastic neutral axis is, but we don't know where the axis is when we're looking at the stresses being completely yielded through the depth of the cross-section. So our requirement for locating the plastic neutral axis is that we have to find the location of a plane through the cross-section that divides the shape into two equal areas. So our requirement is that the plastic neutral axis must divide the shape, meaning the cross-section, into two equal areas. So let's solve for what half of the total area is. My total area for this cross-section is going to be 10 times 2 for the top flange, plus 18 times 1 for the web, plus 6 times 2 for the bottom flange. That's 50 square inches. So half of the total area is 25 square inches. And now one approach to dealing with this is to figure out which of the cross-section elements the plastic neutral axis has to lie within. So it's either going to be in the top flange, in the web, or in the bottom flange. And one way to tackle this is to calculate the areas of those separate pieces. So the area for the top flange is equal to 10 inches by 2 inches, or 20 square inches, which is smaller than half of the total area. So that tells us that the plastic neutral axis is either going to be in the web or in the bottom flange. And if I mentally compute the area of the web, it's 18 square inches. 20 plus 18 is 38 square inches, which is greater than 25 inches squared. So it follows that the plastic neutral axis has to be in the web. So now we need to solve for this distance, y sub p. So I'm going to set the area in compression equal to the area in tension. So if I'm assuming that this is in positive flexure, my area in compression would be the area of the top flange plus the portion of the web that's resisting compression. So the area of the top flange is 10 inches by 2 inches, and then the area of the web that's resisting compression is a 1-inch thick web times a height of yp minus the thickness of the flange, since y sub p is measured to the top of the top flange. Okay, so my area in tension then is going to be everything below the plastic neutral axis. So it's going to be the rest of the web and then the bottom flange as well. So I'll show that portion of my calculation in blue. So the remainder of the depth of the web is going to be 1 inch thick times a total depth from the top of the top flange to the bottom of the web of 20 inches minus y sub p plus the area of the bottom flange. So now I just solve for y sub p. So from that equation above, I can rearrange and solve for yp, and it's equal to 7 inches. And that's measured from the top of the top flange downwards. Okay, so y sub p, 7 inches. So our next task is to solve for the plastic section modulus about the strong axis. So now we know where y sub p is. This is 7 inches. We need to solve for the plastic section modulus. So Z sub x, we said, is equal to the total area divided by 2 times a moment arm between the area that's resisting compression and the area that's resisting tension. So effectively what we need to do is define the location of the compression and tensile force resultants, and then we need to multiply that moment couple by a distance. So our first step is going to be to solve for the centroid of the area in compression, and then we'll solve for the centroid of the area in tension, and that's going to tell us where those force resultants are located on the cross-section. So the area that's resisting compression is everything above the plastic neutral axis. So let me sketch that out. Here's the top flange. There's the web. And here's the plastic neutral axis. Top flange is 2 inches thick, 10 inches wide. The web is 1 inch thick, and the depth of the web to the plastic neutral axis is 7 inches minus 2 inches. One of the easiest ways to deal with this is to make a little table. So I'm going to label my columns as the part that I'm looking at in the cross section, the area of that part, the distance from the plastic neutral axis to the centroid, excuse me, and the quantity A times Y, which will have units of inches cubed. And the pieces that lie in this cross-section are the top flange and the web. So the area of the top flange is 20 square inches. The distance from the plastic neutral axis to the centroid of that piece is 6 inches. And A times Y is equal to 120 inches cubed. For the web, the area is 5 square inches. And Y, from the location of the plastic neutral axis to the centroid of the web, is going to be 2.5 inches. So A times Y is 12.5 inches cubed. Now just finding the geometric centroid of this piece, Y bar is equal to the sum of YA divided by the sum of A. So I'll look at the summation of A and of AY. Sum of A is 25. That's good. We know that this has to equal half of the total area. If this came out to any value other than 25 for this shape, I would know that I messed something up. And then the sum of AY is equal to 132.5. So this quantity is 132.5 inches cubed divided by 25 inches squared, and that is equal to 5.3 inches. And that's measured up from the neutral axis. Now you could have taken a different point as your baseline other than the plastic neutral axis, but I would recommend against it. What we're trying to do is to find the location of the force resultant in compression and the force resultant in tension somewhere down here, and we want to find the total moment arm between those two pieces. So what I just did is I solved for the centroid of this shape, with respect to the plastic neutral axis. So that tells me that here is my compressive force, and this distance is 5.3 inches. So now after I go through the same process for the centroid of the area in tension, I only have to add 5.3 inches to whatever quantity I find for tension. If I had used any other point as my baseline, I would just have to go through a little bit of additional algebra to come up with that moment arm distance between the two forces. So next, let's calculate the centroid of the area in tension. And once again, let's draw a sketch. Here's the web. Here's the plastic neutral axis. And then here's the bottom flange. So bottom flange, 6 inches wide, 2 inches thick. The web is 1 inch thick, and it is going to have a height of 13 inches. I want to solve for the geometric centroid of this shape. So once again, I'm going to make a table. I'm going to use the same column headings: part, area, y, and area times y. And now the pieces that I'm calculating this for are the bottom flange, the web, and I'm going to have to calculate the sum of the area and of AY. So the area of the bottom flange is 12 square inches. The distance from the plastic neutral axis to the centroid of the bottom flange is going to be 13 plus 1, so that's 14 inches. A times y is 168. For the web, I have an area of 13. And then measuring from the plastic neutral axis to the centroid of the web area in tension, I have 13 divided by 2, or 6.5. So A times y is 84.5. So the sum of my area, again, is equal to 25 square inches. That's good. That's half the total area. It needs to be that. And AY is 252.5 square inches. So calculating the geometric centroid here, y bar is equal to the sum of YA over the sum of A. I have 252.5 square inches divided by, that's cubic inches, divided by 25 square inches gives me a length of 10.1 inches, and this is measured downwards from the plastic neutral axis. So the location of the tensile force resultant is somewhere right around there. And this distance is 10.1. So the total moment arm between the tensile and compressive force resultants, little a, is just going to be that distance that we calculated for the centroid of the compression piece measured from the plastic neutral axis, and the centroid of the tension part measured from the plastic neutral axis. So I have 5.3 inches plus 10.1 inches, and that total moment arm is 15.4 inches. So now it becomes very easy to solve for the plastic neutral axis, the plastic section modulus. Z is equal to A over 2, my total area, times 1/2, times that moment arm between the force resultants. So I have 25 square inches times 15.4 inches, which gives me a plastic section modulus of 385 inches cubed. Now, except in very, very rare circumstances, the plastic section modulus is always going to be larger than the elastic section modulus. So that's another quick check that you can do to make sure that things are making sense. All right, next we can solve for the plastic moment capacity of the cross section. And this calculation for the plastic moment is just the yield strength of the material times the plastic section modulus. So our yield strength we said is 36 KSI. Z sub x is 385 inches cubed. And this gives me a plastic moment capacity of 13,860 kip inches. So if you are more comfortable working in kip feet, you can divide that value by 12. And we can finish this problem by solving for the shape factor. And you can either look at this as the ratio of Z sub x to S sub x, or as M sub p divided by M sub y. I think it's going to be easier to look at this in terms of the plastic section modulus divided by the elastic section modulus. So Z sub x is 385 inches cubed, and S sub x measured to the bottom was 283 inches cubed, which gives me a shape factor of 1.36. Now you could also calculate another value using S sub x measured to the top, because we're going to have different values of efficiency depending on whether we're worried about the top or the bottom failing first.